Okay, today we're going to talk about the mole concept and how that relates to the mass, number of particles and volume of any element or compound. And one of the things, as I'm working problems on this stuff, I am going to have the problems already worked out for you. So you might want to, pause the video at that point to make sure you know what's going on, because if not, it'll look like I'm flying through it. But I just want to have the ability to kind of work through this faster and not have you on here for 30 minutes or something like that. So anyways, so what is a mole in chemistry? And a mole is actually a number of things. That's what, when you say to define a mole, it is a number of things. And it's like a dozen. We all know that a dozen is 12 of anything. And a mole is 6.02 times 10 to the 23rd of anything. So if I said, go count out a mole of this, that, what you would have to do is count out 6.02 times 10 to the 23rd of those things. What I want to show you here, and this is called a mole map here, and this mole map, and I actually have it, you'll have this mole map that'll be on Schoology for you to use, and you can actually use this to do any type of mole problem you want. And so it's very useful when you start working mole problems. And again, I'm going to compare it up here to a dozen. So we know that a dozen is a certain number, it's 12 of anything. But let's say we had a dozen oranges, we weighed them out, and we said that a dozen oranges is 2 kilograms. And we also looked at the volume of a dozen oranges, and it was 4 liters. If you know all of these things, you can convert to one to the other, either to a dozen to mass or mass to a dozen, if you know those things are in fact true. And again, we can do that in chemistry, so that's what makes easy conversions from mass to particles to volume to moles, or to moles to any of those things. Let me show you real quick what I'm talking about. We say a dozen is 12 particles. Well, if I said, how many particles is 2 dozen? When you're going with these arrows, you multiply, and when you're going against the arrows, you divide. So if we say we have 2 dozen, 2 times 12 is 24 particles. I mean, that's common sense. A dozen oranges, let's say, again, we weighed it and they weigh 2 kilograms. Well, what if we had 2 dozen oranges? And we go, how many kilograms would that be? 2 times 2 would be 4 kilograms total. Common sense. Same thing over here. We say a dozen oranges has a volume of 4 liters. Well, what does 2 dozen oranges have volume of? 2 times 8 is, 2 times 4 is 8. And if we were going against it, if we said, okay, we had 24 particles, how many dozen is that? It'd be 24 divided by 12, or 2 dozen. Again, over here, if we said we had 4 kilograms of oranges, how many dozen would that be? It would be 4 divided by 2, or 2 dozen. And again, over here, if we say we have 8 liters of oranges, and we say how many dozen would that be? Since we know a dozen is 4 liters, it would be 8 divided by 4 is 2. So again, multiply with the arrows, divide against them. You can do any type of mole problem like this. And the good thing is, if we're talking about masses of oranges and volume, we'd actually have to go measure that. But in chemistry, it's already done for you. So the question is, if you want to know the mass of a mole, what do you multiply by? You multiply by the molar mass of that substance. So what I'm saying there is, these are the atomic masses or molar mass of any substance. And these are relative masses. So hydrogen weighs 1. If you go get 1 gram of hydrogen, you have a mole of hydrogen. You have 6.02 times 10 to the 23rd particles. Took them years to figure this out, and the numbers have changed over time, but now we know that whenever you have a relative mass, you have the exact same number of particles, so they worked for years to figure out how many particles that would actually be. If you go get 12 grams of carbon, you have a mole of carbon, 6.02 times 10 to the 23rd carbon atoms. Now you might say, well, how could 1 mole of carbon weigh 12 and 1 mole of hydrogen weigh 1? Well, carbon's 12 times larger than hydrogen. And we know why, because we know that hydrogen is just 1 proton, whereas carbon is 12 protons and 12 neutrons. And so it's got 12 things in the nucleus versus hydrogen, which only has 1. So again, you get the molar mass of any of those things on the periodic table, you have a mole of that substance, or again, I should say atomic mass, which is molar mass, and you know how many particles you have. Again, the way we'll use this, again, this mole map, is if we say, again, it's common sense. We say 1 mole of carbon weighs what? Look up its molar mass. It's 12 grams. But what would 2 moles of carbon weigh? You would simply say 2 times its molar mass, or 24 grams. We also know that a mole of any gas, and this is just for gases that we're talking about, occupies 22.4 liters. It doesn't matter what the gas is made up of, because the particles are so small and most of the gas is empty space, that a mole of any gas, and this is STP at standard temperature and pressure, would be 22.4 liters. So if we had 2 moles of gas, we want to know how many liters that would be. It would be 2 times 22.4, or 44.8 liters. So again, very useful thing to calculate mole problems. And you might say, well, why is it important for chemists to know how much of any particular substance they have? And you know, here's a good example of why, what we're going to be working on in the future and why you need to know this. This is a mole of sulfur. Now again, when weighed out, sulfur's mass is 32 grams. So this is 32 grams of sulfur here. So I know I have a mole of sulfur. Now this is a mole of iron. And again, I'll look it up on the periodic table. There's its molar mass. It's 56 grams of iron. And so I know I have a mole of iron. Now if I'm going to put these together, if some company says I need you to put these together and make iron sulfide, and I don't want you to waste anything. And so I want to know exactly how much product we're going to get as well. So the fact that I know that I have a mole of each one of these, I know exactly how many particles I have. The next thing I'd have to know is, well, how do they go together? And let's say it's iron Roman numeral 2 sulfide. Well, iron's charge is 2, sulfur's in column 6, its charge is 2. So they would go together in a 1-to-1 ratio. So now, since I know that, if I put these together, heat them up, and they combine, I know that I have the exact same number of particles of both, which is what I need. And then I can add the masses together to know how much what the product or iron sulfide will actually weigh. So that's why it's important to know how much you have in chemistry. All right, so let's go work on some of these problems associated with this. And we could skip all of this. There's a mole map, but I don't like that small version. Again, you know, if I were you, I would always use this one that we will send to you, because on the back of this mole map, there's instructions on how to do every other type of problem in this chapter. So right here, it's got all the directions to do any problem you're going to need to do for this chapter. So first thing we're going to do, though, is we are going to look at the relationship again between moles and particles. So again, we're going from here to here, or here to here. Again, remember, multiply with the arrows, divide against them. And what we're multiplying or dividing by is 6.02 times 10 to the 23rd, because that's what a mole is. I should back up a second and talk about that number. Like, how big is that number? And again, there's some things, I know you can just read these, but it says if you stacked up a mole of soft drink cans, it would cover the surface of the earth to the depth of 200 miles. You know, if you, a mole, and it's called Avogadro's number, which is 6.02 times 10 to the 23rd, of unpopped popcorn kernels, spread them across the United States, but cover it to a depth of 9 miles. And again, you can look at the last one there. So, but here's the thing again, this is a mole of copper atoms. This is a mole of iron atoms. So what that tells you is that atoms are really, really small. They're really small. So again, so let's make calculations here, going from moles to particles and particles to moles. First thing you need to do is how many moles of magnesium is in 1.25 times 10 to the 23rd atoms of magnesium. Write down what you have to start with, 1.25 times 10 to the 23rd atoms of magnesium. Now is where we're going to start using the conversion factors that you worked on in the math chapter. Again, we'll use these for the next couple of months. And so what you do is you're going to go from atoms to moles. We can do that in one step because, again, we're going from here to here. And if you're going from here to here, you can do that in one step. And later on, next time, I'll show you how to go from, say, particles to mass, which would be a two-step problem. All right. So, again, we're going to go from atoms to moles. So put moles at the top of your conversion factor. Remember, we always got to cancel out our preceding unit to go from one unit to the other. So we got to cancel out atoms, so we'll always know what goes here. It doesn't matter what you put in the conversion factor, they must be equivalent. So we always say 1 mole is how much of something. 1 mole is either a certain number of atoms, a certain mass, or a certain volume. 1 mole is always 6.02 times 10 to the 23rd atoms. Now you multiply across, then divide. So you multiply by 1 divided by 6.02 times 10 to the 23rd. We're going to use sig fig. Sig fig rules as you're doing calculations in chemistry are actually simple. Go to the original number, That's got 3 sig figs. That's what you need in your final answer. So your answer would be rounded to 0.208 moles of magnesium. And the mole map will always be correct as well. What we did was we went from particles, which is atoms. Again, particles could be atoms, molecules, or formula units. Formula units, again, if you're confused by that term, that's the smallest part of an ionic compound. I think most of you would want to call that a molecule, but the smallest part of a molecular compound between two nonmetals is called a molecule, like CO2 would be a molecule. But the smallest part of an ionic compound, like NaCl, salt, is actually called a formula unit, not a molecule. So what we did there, we went from particles to moles. Again, we went against the arrow, so we divided by 6.02 times 10 to the 23rd. That'll get you the right answer there. Now next, we got 2.12 moles of propane, which is C3H8. So now we're here. We're going to go, how many particles that? We multiply by 6.02 times 10 to the 23rd. So again, we write down how many moles we have. We're going to molecules, so we put molecules at the top of our conversion factor, moles at the bottom, because you got to cancel preceding units. We always do that. And then again, we take 2.12 times 6.02 times 10 to the 23rd. We get 1.28 times 10 to the 24th molecules of C3H8. Again, this would always be correct because you're going from moles to particles. You're multiplying by 6.02 times 10 to the 23rd. Now we're going to talk about the relationship between mass and mole. Okay, and again, if I say, so we're going to go from moles to mass, and in your in this mole map, it says formula weight. I always mark that out. Formula weight means molar mass or atomic mass. It's the same thing, so I always say molar mass. So if you're going from moles, you want to know what a mole weighs. You multiply it by the molar mass of that element or compound or formula unit. That's all you have to do. So first thing, so we need to establish like how we figure out what a mole of anything weighs. So if I'm just asking you, what is the mass of a mole of argon? Okay, you don't need the mole map to do that. You simply look up argon, and it weighs 40 grams. If you get 40 grams of argon, you have a mole of argon. You can say that for all monatomic elements on the table. Most of these elements exist as single atoms. Like again, if I look up, a mole of iron, what does it weigh? Since these exist as individual iron atoms, it weighs 56 grams, or 55.8 grams. You get 55.8 grams of iron, you have a mole. But there are some elements that's not the case. So if I say, what does a mole of chlorine weigh? And you look up chlorine, which weighs 35.4, and you go, okay, 35.4 grams of chlorine is what a mole of chlorine weighs. But chlorine gas does not exist as individual elements. It's what we call a diatomic molecule. So all the chlorine gas that would be floating around is Cl2. So if we want to count, we'd be counting out 2 at a time before we got to a mole. And so we'd have to say 35.4 times 2 is the molar mass of chlorine. Now, there are 7 elements on the periodic table, and I'm going to rewrite them for you just so you know, again, what I'm talking about. And we call them the Brinkhoff elements. And someone over time, I don't know who's done this. I don't know if it's associated with Lake Travis or some other place. But I've always used the term Brinkhoff to talk about the elements that exist diatomically in their normal state. So there's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. What do I mean by that? It's a Brinkhoff element. It's just a way to remember the ones that are diatomic. And it may seem silly now, but over time, we'll repeat this over and over again. I'll go, is it a Brinkhoff element when you're talking about its mass? So what do I mean by that? All the oxygen floating around the room, oxygen weighs 16. The molar mass of O is 16. But if I say, what is the molar mass of oxygen floating around the room, you'd be counting them out 2 at a time, because there aren't any oxygen molecules in this room that are just individual oxygens. So it'd be O2. So the molar mass of oxygen is 32. The molar mass of hydrogen floating around the room. Again, it doesn't exist as one hydrogen atom. It exists as 2 stuck together. So its molar mass is 2. And nitrogen, 70% of the room is nitrogen. And the nitrogen floating around here it's not stable as one nitrogen atom. It's actually stable as 2 of them stuck together. And so nitrogen weighs 14. But if I say, what is the molar mass of the nitrogen floating around the room, since we know, again, it exists as N2 molecules, it would weigh 28. So again, Brinkhoff elements is another way to look at where they are. Some people say, go to column 7 and make a 7, and you found your Brinkhoff elements. There they are, right there. And the only one, go to 7 and make a 7, and the only one missing is hydrogen. So those are diatomic elements. They do not exist as individual atoms, and that's a very important thing to know. We keep talking about that over and over again. Now, if you go, What about what's the molar mass of a molecule? How do you figure that out? Well, if we're counting out the molecule nitrogen dioxide, which would be 1 nitrogen and 2 oxygens, and we want to know what a mole of the whole thing weighs, we've got to add up the masses of everything in that compound. So nitrogen weighs 14. You might go, I thought you said it was N2. That we're talking about when it's by itself, it's N2, not in a compound. So in this particular compound has 1 nitrogen in it. So it's got 1 nitrogen, it weighs 14. I got that again from the periodic table. It weighs 14 grams. And then oxygen, there's 2 for every molecule of nitrogen dioxide, and 1 oxygen weighs 16, so that'd be 16 times 2. It's 32 grams. Add them up, 46 grams there. All right, the next one, ammonium carbonate. Well, again, if it's an ionic compound, that actually, the smallest part of that is called a formula unit. You'd have to cross the charges to put that together. You cross them. NH4 is ammonium. It's got a +1 charge. CO3 -2. Cross the charges, you get NH4 parentheses 2 CO3. And then if you want to know what a mole of all of that weighs, you got to add up all the atoms that are in it, add up all their masses, and then you'll have the molar mass of ammonium carbonate. So there, 2 outside the parentheses means there's 2 nitrogens. So its mass is 14 times 2. There's 8 hydrogens. 2 times 4 is 8. Hydrogen weighs 1, so there's 8 times 1. There's 1 carbon, it weighs 12. Oxygen weighs 16, and there's 3 of them. Add all that together, you get 96 grams. Now, again, if you go to the lab or the storage room and get 96 grams of ammonium carbonate, you have a mole of ammonium carbonate. That's why you need to know that. What is that? It is 6.02 times 10 to the 23rd formula units of ammonium carbonate would be what you have. Next one, barium chlorate hexahydrate. This means that it is attached to water. Some molecules are very attracted to water. And so that particular molecule is stable as barium chlorate. First of all, barium's charge is 2, chlorate is ClO3 -1. You cross the charges. You remember, you bring a number down larger than 1 below a polyatomic, you got to put it in parentheses in the number. And so that's barium chlorate. Hexahydrate means it's got 6 water molecules attached to it. So what you got to do now is you got to add all this stuff up. It's got 1 barium, which weighs 137. Again, if you're wondering where am I getting that number from, there's barium right there. It weighs 137. It's got 2 chlorines. They weigh 35.4 apiece. There's 2 of them because the 2 outside the parentheses multiplies everything in there by that number. And then 2 times 3 oxygen. So oxygen weighs 16. It'd be 16 times 6. Now over here, this does not mean multiply these 2 together. This dot here simply means that barium chlorate has 6 water molecules attached to it. So when we talk about the total mass of this, we've got to add all this stuff together. So if it's got 6 water molecules attached to it, the 6th here, as a coefficient, multiplies everything over here by that number. So 6 water molecules would have, 6 times 2 would have 12 hydrogens in it. Each one of them weighs 1, so it'd be 12 times 1. And it would also have 6 times 1, or 6 oxygens over here in 6 water molecules. So it'd be 16 times 6. You have to add all those together, multiply 35.4 times 2, 16 times 6. Add it all up, you have 412 grams would be the molar mass of barium chlorate hexahydrate. Again, some compounds are very attracted to water, and that's what they're stable as. So barium chlorate hexahydrate. Now, when we talk about the mole mass, mole volume relationships again, here's how you do that. Again, we go back to our mole map to do this, and it says how many grams would 9.45 moles of nitrogen dioxide weigh? So we're here, we're at moles, and we're going to mass. We've got to multiply by the molar mass of that substance. So write down what you have first. You got 9.45 moles of, again, dinitrogen trioxide, that's N2O3. We're going to go from moles to grams, so go to grams here. We can do this in one step because, again, we're going from moles to grams. Only if we were going from, say, grams to particles would it require more than one step. So, again, so we're going to grams. Cancel out your preceding unit. Always cancel out moles. Go 1 mole weighs how many grams? Again, look that up on the periodic table. You're looking up, again, the mass of nitrogen is 14 times 2 because there's 2 of them. And oxygen weighs 16 times 3 because there's 3 of them added up, and it weighs 62 grams. So, what do you do now? If 1 mole weighs 62 grams, it should make sense to you that 9.45 times 62 will be almost 10 times the mass of 62 grams. So 9.45 moles times 62, 586 grams of N2O3. Notice again, sig figs are 3 there, 3 in our final answer. And again, we're doing exactly what the mole map would say to do, because the mole map says if you're going from moles to grams, you're going with the arrows, you multiply by the molar mass. Again, you multiply with the arrows, and so that's how you get our answer there. The next problem, 0.012 moles of K2CO3 potassium carbonate. Again, you'd have to put all that together to know that cross the charges and it's K2CO3, potassium's charge is 1, carbonate's charge is 2. And then you got to look up the mass of 2 potassiums. Potassium weighs 39, there's 2 of them. 1 carbon, it weighs 12, and then 3 oxygen, 16 times 3. Add all that up, you get 138 grams of K2CO3. So again, we're going from moles to grams. So we write down what we had to start with. We're going to grams at the top of our conversion factor. Cancel the preceding unit. We always put 1 mole is how many grams. We look that up in the periodic table, add all that up. 1 mole of potassium carbonate weighs 138 grams. And so number of moles we have times the mass will get us our answer there at 1.55 grams of K2CO3. Same situation there, again, going from moles to grams. If we're going from grams to moles, you divide by molar mass. Question down here at the bottom, I want to do this one again before we move on. 75 grams of nitrogen gas. So that's what we're starting with, but notice, if you don't realize that nitrogen gas is diatomic, it does not exist as individual atoms, you don't write N, it's N2. And it'll affect the mass of a mole of N2. So we're going to go from grams to moles of N2. So we'd say 1 mole of N2 is 28 grams because, again, nitrogen weighs 14, but there's 2 of them. And then 75 divided by 28 will give us 2.68 moles of N2. And again, if you look at where you're at on the molar map, we started, in this case, we started with mass, and we're going to moles, and we're going against the arrow we divide by the molar mass. In this case, it's of nitrogen. So again, this would always be correct. The mole map would be correct to do that problem. And then the last thing for today is going from moles to volume and volume to moles. Again, we're doing this part of the problem here. If you're going from moles to volume, you multiply by 22.4. And if you're going from volume to moles, you divide by 22.4. So, so real quick, and this is only for a gas if this is true. It says we've got 0.6 moles of SO2. How many liters is that? So we always start off with whatever we start with at the top of our conversion factor there. We're going to go to liters. We cancel out the preceding unit. We say 1 mole is how many liters. And again, this is always a constant. A mole of any gas is 22.4 liters. So going from moles to volume or volume to moles, you either multiply or divide by 22.4. That never changes. So 0.6 moles times 22.4 is 13 liters. Again, we went from moles to liters. We're multiplying by 22.4. So we got 13 liters as an answer because, again, that's 2 sig figs. We have 2 in our final answer. And again, here we're going 67.2 liters to moles. Again, starting with liters, going to moles, we can do that in 1 step. Again, because you're going from liters to moles or moles to liters, we can do that in 1 step. 1 mole at the top, liters at the bottom. 1 mole is always 22.4 liters. Again, that's given to you on your mole map. You don't have to memorize that. And then multiply, cross, and divide. In this case, 67.2, get cancel that unit out. Divided by 22.4 will be 3.00 moles of SO2 because of the 3 sig figs there. You can check this with your mole map to make sure that it would always be accurate. And so in this case, we went from volume to moles. We're going against the arrow. We divide by 22.4. That's what we did. That's what we got our answer there. Again, hopefully it's a lot of stuff. Mole volume, mole mass, mole particle problems. But again, use the mole map, make the problem simple. Good luck.